This is Jack Jackson. In this video, we're going to talk about how to find the equation of a tangent line to a curve. Okay, so if we're given a function f of x, we want to find the general form, a general formula for the linear function which best fits this given function f of x near a particular point where x equals a. Of course, if x equals a, y equals f of a on this given function f of x. So the first thing we want is we want the line to match the function at that point. So that means both the line and the function will have this point a f of a on them. Furthermore, we want the two graphs to follow each other closely as possible near this point. So to do this, we make their slopes the same, and the line we're looking for then is the tangent line to the curve at this point. So let's review a little bit of pre-calculus algebra here. So how do we find the equation of a line given a point on the line and the slope of the line? So first of all, remember that functions that are linear have constant slope. So if we take a specific point we know that's on the line, let's call it, for the moment, let's call it x1, y1. And then we want to take any other point on the line. Let's think of it as a variable arbitrary point xy. That's the coordinates of that point. Then the slope is constant, and we're going to let that be represented by the letter m as usual. So we have m, which is delta y over delta x, is a constant. So that's y minus y1 over x minus x1 is the same number every time, which we call m. Well, we simply solve this for y to get us a nice form of equation here. So we're going to take this equation, m equals y minus y1 over x minus x1, solve for y. To do that, we start by multiplying both sides of the equation by x minus x sub 1. That gets y minus y sub 1 equals m times x minus x sub 1. You'll often see the formula left like that. And then sometimes we'll add 1 to both sides, y1, y sub 1 to both sides to get y by itself. And we get this form of the equation, which is y equals m times x minus x1 plus y1. And this is called the point-slope form of the linear equation right here. Some people will also call this middle form the point-slope formula. So here's the point-slope form of a linear equation where x1, y1 is some specific point on the line, any specific point on the line, and m is the constant, which is the slope of that line. Now, first of all, notice that the point-slope form of a linear equation is not unique. So there's a different version of this for every point that's on the line. Of course, there are infinitely many points on the line. So there are infinitely many different point-slope forms for the linear equation. So there's this point that it's centered at, x1, y1, and you put any point as long as it's on the line, x-coordinate right here and y-coordinate here, and the slope of the line here, then all the points that make this equation true will be the points that are on that line. Okay? And of course, this works for anything except for vertical lines, which, of course, the slope is undefined. Now, the line that we're looking for, let's remember, is going to be related to this function y equals f of x. It's going to go through this point a f of a. So this point x1, y1 is actually a, comma, f of a. And, of course, the slope is the slope of the tangent line, which we know is the derivative. So we're going to substitute the slope equals f prime of a. Okay, so substituting those two things in our formula above, we replace m by f prime of a, we replace x1 by a, and we replace y1 by f of a, and here we have the equation of the tangent line. So all we need to do is, if we're just given an a value, we need to find the y value on the original function, which will also be the y value on the tangent line when x equals a. So find that point. And then we find the slope at that same x value, and that's the derivative at that x value, and that will be the slope or the coefficient right there, and we just plug it in. So let's do an example. Let's see if you can do it actually. Before we do that, let's point out a couple of things. So notice that the linear approximation is perfect at the point of tangency. In other words, what we're trying to say is that f of x, let me be explicit about that. So we're saying that f of x is approximately the same as this. Okay, that is the approximation there. Okay, so we're saying that the function is approximately equal to this linear thing here, which is the value of the tangent line. Now, this approximation is absolutely equal when x equals a. See, if you plug in a here, you get a minus a is 0. This whole part goes away. You just get f of a equals f of a. Perfect. Okay, as x is close to a, then this approximation is very good. As you get farther and farther from a, then that approximation gets less and less good in general. Okay, so in general we want to see that. So let's see if you could do this problem right here. Find a linear approximation to the function f of x equals x cubed near x equals 2. In other words, find the equation of the tangent line. So another way to say that same problem would be find the equation of the tangent line to f of x equals x cubed when x equals 2. Okay, so I would like you to do that one yourself, and then maybe we'll come back and check it here in a minute. So work this one yourself, come back when you're done, and check it. Press pause now. Okay, so now you're back. You worked this out hopefully on your own, where we have the function f of x equals x cubed, and we want to find the linear approximation or the equation of the tangent line where x is 2. Okay, well, first step is to find this, well, we've got the a is 2. So now we need to find the f of a. Well, that's pretty easy. We just plug in 2 in place of the x here. So we get f of 2 is 2 cubed, which is 8. So that says the point 28 is our a f of a. That's our point x1, y1. And so we can plug the 2 in here for a and 8 in for f of a. Now we need to find f prime of a. Now, okay, let's do this a couple of ways. First of all, let's do it approximately. Well, one way we can do it approximately is to put it in our calculator. So on the left, you'll see an older version of a TI-84, and you push Math 8 and get numerical derivative. You put in your formula, x to the third power, comma, your variable x. That's the derivative with respect to x, comma. You put in your a value, the specific x value we're finding the derivative at, which is 2, close parentheses. This defaults to an h of 0.001, and you get 5 zeros and a 1. You could get a slightly better version if you put in a smaller h, perhaps. So it looks like maybe 12, maybe close to 12 here. Okay, I did it on a TI Inspire. This is a CAS version, so this is going to give me an exact answer. And the syntax goes like this. This is the syntax on the newer versions of the TI-84 as well. It's d over dx, fill in that blank with an x, fill in this spot right here with the formula, x cubed, and this will say x equals, and then you put in the a value right there, which is 2, and on the TI-84, the newer one, it's going to give you the same thing as this because it's using the symmetric difference quotient. Over here on the CAS version of the calculator, it's actually doing some shortcut rules, are some things dealing with our limit laws and so forth and figuring this out. Exactly. So it turns out the exact value is 12. How could you find that exact value? Know for sure it's 12. Well, to do that, we need to use the definition of the derivative along with some algebra and some limit laws to actually compute the limit. So let's go ahead and do it that way. Let's see if I can get this up on the same page as the other. Okay. All right. So f of a plus h minus f of a over h. Take the limit as h goes to 0. That is f prime of 2 of a in general, right? Let me just say that. So f prime of 2 is this. Okay. Just make it a little bit longer. All right, so let's see what we're dealing with here. Let me just do a little formatting here to make this a little bit easier to see. Okay, so so this is the general definition. F prime at A is the limit as h goes to 0 of f of A plus h minus f of A over h. That is so crucially important to calculus. You definitely need to memorize that. Now, what are we doing? We're doing with this, that's in general. So our thing we have is a specific function f, which is f of x equals x cubed, and our A is 2. So here's f prime at A for our particular one, and then f prime at 2 is here. So for our particular function, it's a plus h cubed minus a cubed over h. Now, for specifically when a is 2, that's 2 plus h cubed minus 2 cubed over h. 2 cubed is 8. So here's our basic difference quotient, and then the limit makes it into a derivative. Okay, now to get a better handle on this, let's see. Let me zoom in a little bit. Maybe you can see it better. Okay, we're going to have to cube this out. So I'm going to think of this first of all as 2 plus h times 2 plus h times another 2 plus h. 2 of the 2 plus h's is 2 plus h squared. So square that out, square the first, square the last, multiply, and double it in the middle. Oops, that's a mistake. That should be 4. And I may or may not have it right going on from there. Let's see. And then to multiply this out, we multiply out distributive again. H times h is h cubed. H squared is h cubed. 2 times 4 is 8. Okay, let's see if we can get the h term. This is 4h plus 8h is 12h. And the h squared term, let's see, there's h squared times 2. So that's 2h squared plus 4h squared is 6h squared. And then h times h squared is h cubed. So I believe that's correct. And then the 8 and the minus 8 cancel. So notice we're doing a lot of algebra steps here. So we're just using the distributive property to multiply all this stuff out. Now we're combining like terms here. Now we notice everything in the numerator has an h, so I can factor that out using the distributive property. And since h is not 0, but only approaching 0, h over h is not 0 divided by 0. You can cancel that out. It's 1. So that leaves this other factor, 12 plus 6h plus h squared. Now that's just a polynomial in h, so that's continuous. So I can just plug in 0 for h here and here. These terms are 0 plus 12 is 12. So in fact, yeah, the derivative really is 12. Okay. So let's so the slope is then the derivative at 2, which is 12. And so the equation of our linear approximation, or in other words, the equation of the tangent line, is y equals f prime of a times x minus a plus f of a. F of a is f of 2, which is 8. F prime of a, we just found out, is 12. And of course, the a is 2. So there's the equations you see in the box. That's the point slope formula, where the slope is 12 and it goes through the point 2, 8. That's the point of tangency. Now, you might want to write this in a couple other different forms. That's sort of this is a form, in this particular one, it sort of makes more sense. This is probably the best form in one sense because it's in the context of centered at this point of tangency, and at the point 2,8 is where it is best, well, it's perfect there. And near 2,8, it's where it's best approximation of the original function. Okay, so we would say f of x is approximately 12 times x minus 2 plus 8. Now, we could also distribute here and combine like terms to get 12 times x is 12x. 12 times negative 2 is negative 24 plus 8 is negative 16. And that's the slope y-intercept form, or sometimes just called the slope-intercept form. The slope you can still see is the coefficient here, which is 12. And the y-intercept, when you plug in x is 0, you see this term goes away and you just get negative 16 for y. So we see that that goes through the y-axis at 0, negative 16. There's also a slope x-intercept form, or factored form, that's very nice. We factor out that leading coefficient of 12. 12x divided by 12 is just x. Negative 16 divided by 12 is negative 4/3. And so now we see that if x is positive 4/3, then y will be 0. 4/3 minus 4/3 gives you a y of 0. So that's the x-intercept, 4/3, 0. So there's a slope y-intercept form, there's a slope x-intercept form. Those are unique for a particular line because it only has one y-intercept and only one x-intercept. But this point-slope form is not unique. You could put in any point that's on the line, put in its x and y and replace it in place of the 2 and the 8, and you would get an equation of the same line. So all of these are equations for the same line. They generate the same set of ordered pairs that make it true, so they generate the same table, they generate the same graph. And of course that graph is a line, and it is the tangent line. Let me go ahead and do one more thing here. Let's graph this. I think the original function was y equals x cubed. And then the tangent line was, let's say we use 12x minus 16. Now if we did this right, we should see the point of tangency. Let's actually put a point there. The point of tangency was 2, 8. And so we see that we see a perfect fit there, and it veers away from it as you move out from that point. So nearby this point, there's not much difference in the red tangent line and the blue original graph. As you get further away, then especially like way down in here, they're not at all alike. But right here they're pretty close, and of course they're perfectly the same, only right there at that one point. Okay, so nearby, very close to that. So let me copy that, put it over here. Okay. And then let me also do a couple other things and show you something once again about this local linearity idea. If we zoom in on this point of tangency, so we've zoomed in, still you can see they're going to be pretty good approximations, say between 1 and 2. Let's just let me change. I'm going to leave a square window here and just go for a window here from say 1 to 2, and let's just go from 0 to 15, let's say, for y. Now this won't be a square scale anymore, and I need to go to 2. I need to go to the right of that 2. Let's see, so 1 to 3, let's say. So again, you can see some deviation here between the original graph and the tangent line, but right in here you're going to see a lot closer. So if I zoom in, say just on this part of the graph, again you see some deviation, but if you start looking at the scale here, this is a pretty small amount. As we zoom in even closer still, it gets harder to tell the line and the original graph apart. And if I zoom in, say on this part here, well, it gets harder and harder to tell them apart. I'd have to really distort the scale to see the spacing there. So this is what we call what we mean by local linearity. If we zoom in on on any differentiable function near the point of tangency, it's going to look a lot like the tangent line. See, if I erase that one, see there's the original graph, looks just like the tangent line, at least to the eye here, right? And of course, as we zoom out, then we see it's looking Yeah, zoom out. Whoops, let's zoom back in. Okay, so as we zoom out, then we start to see, as we get further and further point of tangency, now it's not looking at all like the graph, right? And it may eventually cross back over here, but at least nearby it's starting to really deviate from it quite a bit. But as long as you stay in here close, it's a very good approximation.